us. And then we have David today as a speaker. Let me quickly introduce David in case you don't know him. He's a postdoc here at ETH and completed his PhD also here at ETH in 2018. And his general research interests are rotational seismology, planetary seismology, and signal processing. And today he will be talking about a recent publication of his about wave type fingerprinting with 6-component data. So yes, David, the stage is yours.
Yes, so thank you very much, Sebastian, and thank you for having me in this seminar. So as Sebastian has said already, so the method that I want to introduce today is what we call wave type fingerprinting. And you can really see an example of this already here on the right, where we have a 6-component seismogram on top here. So basically a recording of both translational and rotational motion. And then on the bottom, you can see a very colorful representation of the wave types that are contained in this seismogram. So both as a function of time and frequency. And this is basically obtained in a fully automated fashion with this method, wave type fingerprinting. So the way we would typically do this is we would basically let experienced seismologists just pick thousands and thousands of seismograms manually, and then basically throw these picks and the waveforms at some convolutional neural network or something similar, and then try to let this network basically find a model that can predict arrival times of different waves. And what I want to show today is actually that if we have these additional measurements of rotational motion, we don't need to do this because the information on the wave type is already contained in the measurement itself. So each wave type has its own or leaves its own fingerprint in the motion of the sensor. So what I want to show today is basically this. So I will very briefly, without going into too much detail, introduce the methodology that we're going to use, which is based on polarization analysis. So it is an extension of conventional 3-component polarization analysis. And then I really want to focus on the applications. So I will show 3 examples. The first one will be an example from global seismology. The second example will be from seismic exploration. And the third example will be the analysis of the ambient seismic noise field. So let's dive into it then with a little bit of theory. So as I mentioned, basically this method is based on polarization analysis. And when I talk about polarization analysis, I mean the analysis of the 3-dimensional motion of a seismic sensor. So how does a seismic sensor move in 3-dimensional space when we're recording a seismic wave field? And you can see this very simple animation here on the right for 3 isolated wave arrivals of different wave types and the motion of the sensor in 3-dimensional space. Now, by doing polarization analysis, what we can do is we can really infer on the ellipticity of the motion. So we can distinguish, for example, between linearly polarized body waves and elliptically polarized surface waves. We can infer on the propagation direction of the wave, given that we know the wave type. So as you can see here on the bottom for P waves, the polarization will be parallel, of course, to the propagation direction. For S waves, it will be orthogonal. And we can also, if we have knowledge on the propagation direction, we can infer actually on the wave type of a measurement. So say we assume that our waves are coming perpendicularly from below our sensor. We know that basically P waves will be mainly the motion in the vertical component and S waves in the horizontal component. But you can see that there's quite some ambiguity in this type of polarization analysis, 3-component polarization analysis. And what we have shown in the past is actually that we can resolve quite a lot of this ambiguity, or basically all of this ambiguity, if we include additionally rotational motions in the polarization analysis. And you can see in here an animation again of basically 6-dimensional or 6-component motion of the ground for these different wave types. Of course, the rotational motions here are a bit exaggerated. And what we have showed in the past is that actually this 6-component motion is unique for each wave type. So we don't need any prior information in the propagation direction to really guess the wave type of a recorded phase. Then we can resolve the 180-degree ambiguity that is inherent to conventional 3-component polarization analysis. We can also resolve the sense of rotation of the ellipticity of the motion. So we can see, for example, for Rayleigh waves, if the motion is prograde or retrograde. And this is probably something that you have heard as you're all involved in spin. The rotational motions, they scale with the slowness of a wave. So by having a combined measurement of translation and rotation, we can infer on the phase velocity of local waves as well. Now, how do we do polarization analysis in practice? And here we'll really do this very short, very quick. So typically polarization is a time and frequency dependent phenomenon. So it makes sense to actually analyze it also in the time frequency domain. And so what I first do typically is I compute the time frequency representation of our seismogram. And here I use the S transform, but you can basically use any kind of time frequency transform to get this transformation. And then we will analyze basically the motion of the sensor, the six component motion of the sensor in a time frequency window that you can see here. And within this time frequency window, we form the so-called covariance, data covariance matrix. And then if we want to infer on polarization states of recorded waves inside this time frequency window, what we do is we do an eigendecomposition, and then basically the eigenvector, which is associated with the largest eigenvalue, will contain all the information of the polarization of this wave. So basically this principal eigenvector then describes an ellipse in space. So here, this is a bit of a simplified plot here on the right, because we're just in 3 dimensions here, but we would have an ellipse in 6 dimensions, which is a bit difficult to picture, but basically the math behind it is the same. And basically this eigenvector, so the real and imaginary parts would correspond to the major and minor semi-axis of this polarization ellipse, which contains all this information on the wave type, ellipticity, and the propagation direction. And in turn, if we're looking at 6 component data, also the information on the propagation velocity. So what we want to do now is actually use this information to really automatically classify the wave types that we are recording. And for this, actually, we can analytically derive what this ellipse would look like for different wave types. And you can see here this analytical models for different wave types, P, S, Rayleigh, and Love, so horizontally and vertically polarized shear waves and surface waves. And basically these models, as you can see, they have 6 components. So this is basically the relative amplitude of the motion in each of these 6 components that we're measuring. They are complex valued, meaning that they have a real part which corresponds to this major semi-axis of the ellipse, and an imaginary part which corresponds to the minor semi-axis of the ellipse. And now they're actually a function of a set of wave parameters, which is the propagation direction and the velocity of the wave. Now I really don't want you to worry too much about the math inside here. So all these parameters that we have, but what you should actually take from this is that each of these models is unique for each wave type. So it provides us with a template for a fingerprint for each of these waves. Now, if you look closely, you can see that SH waves and Love waves actually have the same fingerprint, because basically Love waves are just horizontally propagating SH waves. Now, what we want to do is actually we want to fit these models to our data, to these polarization states that we extract from our data with the eigenanalysis. And what we could do here is basically just trying to fit those using a grid search. So just parameterize these models and try to find the models that best fit our data. Now, this would, of course, be extremely expensive to do, because we would have to do it at each time frequency point, which is extremely expensive as well, of course. And the alternative to this is, of course, to resort to some sophisticated tools to do this classification. And what we're going to do is we're going to use a bit of machine learning for this, which is what I want to introduce here on the next slide. So actually, this is not any kind of fancy machine learning like convolutional neural networks or anything like this. It is really a very simplified approach that I use here, which is a support vector machine. And the advantages of this classification algorithm is that it is quite simple, memory efficient, and it can be really easily applied to high dimensional data, but also to large data sets very quickly, which is the major benefit here. So you can see basically how this classification works here for a very simplified toy example on the right, where we have a two-class problem. We have this one class, which is basically denoted here by these green circles. And then we have a second class, which are the red diamonds. What we're trying to find is basically a plane that separates these two classes. So these are labeled data sets. So it's a supervised learning algorithm that we're using here. And of course, now in theory, we would have infinitely many lines that could perfectly separate our data here. And the way the support vector machine algorithm works is we're really trying to find the one line that optimally maximizes the margin between these two classes that we have here. And of course, in theory, we can expand this, or we can do some tricks to make this feasible also for classification problems where our two classes are not linearly separable. So what I do now is basically I train this support vector machine using completely random polarization models. So this would be the models, these mathematical models that I showed on the previous slide. So I generate 5,000 of these random models for each wave type, and I parameterize them with a completely random parameterization drawn from uniform distribution. So this means that actually for the training of our classifiers, we don't need any actual field data. We just use these physical models of elastic waves at the Earth's free surface here. Then as features, we use the real and the imaginary parts of these models. So this would give us 12 features because we have 6 components and real and imaginary parts, of course. And we're trying to distinguish between 5 classes here. So one would be a noise class, which would be basically trained by just using completely random elements for each of these features. So this would be basically unpolarized signal. And then we have the different wave types, P, S, and surface waves. Now, to evaluate how this classifier performs, to really confirm that these fingerprints are unique for each wave type, I did this very simple analysis with just a test data set where I additionally generated 5,000 more of these random polarization models. And then I checked if the class that my trained classifier gives them actually corresponds to the actual class that we would expect, that we used to generate the model, of course. And you can see basically a plot of what we call a confusion matrix here on the right. So we have the true label of each sample in this data set on the y-axis, and then the predicted label on the x-axis. So what we would like to see typically is that now all our classifications lie on the diagonal of this confusion matrix. And you can see that really only very little confusion happens here between the different wave types. The only confusion that happens here is between SH and love waves. This is, or significant confusion that happens is between SH and love waves, which is of course what we would have expected here. Now, what is important to mention here is that this would actually not be possible with just 3-component data, because with 3-component data, we can't distinguish, for example, between P and S waves, because both of those are just linearly polarized, and we don't have the information in there that we need to really distinguish between the two. Okay, so this brings us actually to the first example, which is really just a showcase of how we apply this method to a field data set. And this field data set is actually an earthquake, a teleseismic earthquake, which was recorded on the ROMY ring laser in 2018. So this was a very large magnitude earthquake that occurred in the Gulf of Alaska in 2018 and is recorded here on this multi-component ring laser observatory close to Munich in Germany. And you can see basically the recorded ground motion here, so translational motions on top, and the rotational motions measured by this ring laser here on the bottom. And now we apply this fingerprinting technique, so where we actually trained this model using completely synthetic fingerprints, and we apply it to this data. So again, this is the 6-component recording, now everything plotted on top. Then this is a time frequency representation of just one of these 6 components, where you see high frequency body waves rolling in first, and then you have a dispersive surface wave train here trailing behind it. And here is now actually the classification. This is what we've already seen on the title slide. With this support vector machine classifier that has actually never seen any real data. So this is purely based on the 6-component motion here. So you can see what it classifies here as the first motion is blue. Blue corresponds to P waves. So we have these 3 distinct P wave pulses here in this data. And then we have something that is red and green, which would be shear waves. So this would be the shear wave arrival. And then yellow here would be Rayleigh waves. So you can see this dispersive wave train here, which would be Rayleigh waves with some law of wave energy, so SH type of motion beforehand. Now, a question that I've been asked quite a couple of times before is, can we do this for events or for waves that are overlapping in both time and frequency? And the answer is actually yes, we can do this, but only if actually the polarization states of these 2 waves are close to orthogonal to each other. And this is, for example, the case for Love and Rayleigh waves. So what we can do is we can apply the same classifier not only to the first eigenvector of our covariance matrix, but to the second eigenvector. And this is what you see here. And what you can see is basically that below this Rayleigh wave train, we can see quite a bit of green dots here, so which would be love wave energy. So here we can say that basically this energy that arrives here is a mix of both Rayleigh and love wave energy. And also here beforehand, you can see that below this love waves, there seem to be some Rayleigh wave energy already. And then what we can do, we can actually go one step further, and we can really start to dissect our seismograms and decompose it into different wave types. So basically now we try to apply filters based on this classification that we've obtained to really separate this seismogram into different components. Then we apply the inverse S transform and look at the waveforms separately. So this is what we do here. So again, the input data here on top. And then you can see here that I basically try to just pull out the P wave component of this seismogram. So we separate these seismograms into different wave types. And now the vertical lines that you see here in this seismogram basically correspond to predicted arrival times of some key phases that I model with ray tracing in just one of the standard Earth models. And you can really see that these arrival times, they seem to match quite nicely with the arrival of these pulses, of these P wave pulses in our separated data. So this really highly facilitates the interpretation of our seismogram. So we could think about, for example, algorithms that automatically pick different phases based on these kind of decomposed seismograms, or it could potentially help us to really identify exotic phases in our seismogram that are difficult to just see in the raw data recording. Of course, it would be nice to have more than just one seismogram, but I mean, hopefully in the future we will have lots more of data to analyze and do this kind of separation. Now, this is basically the separated S-wave component. So you can see here that basically the S-wave arrival is quite nicely pulled out of this seismogram. You can see there seems to be some kind of small pulse coming in here just after the P wave arrival, which could, for example, be mode converted P to S phases and so on. So really what we can do with this still needs to be further explored. But I think there's quite some interesting information contained in here, which will hopefully help us to ask or solve or answer some of the important questions in seismology. Then this is then the Rayleigh wave component here. Again, you can see the clear dispersive behavior here, where we have low frequencies arriving first, and then we go to higher frequencies at later times. And then this will be the love SH wave component of the seismogram with the clear love wave arrival in here. So this was the first example. So just to kind of show you a bit how this method works. Now I want to go to the second example, which would be an example from seismic exploration. Here we had a collaboration ongoing with Total, which actually ended in December now. And there actually the main interest would in this method would be, can we use it to suppress surface waves in land seismic exploration data? And really surface waves, they pose one of the major challenges to land seismic exploration because they can cover up some of the reflection signal that we're actually interested in that comes from subsurface reflectors of interest. And you can see an example here. So for those of you who are not familiar with land seismic exploration data, so this would be basically a data matrix where each column in the matrix would be a seismogram, a color-coded seismogram, and the source would be located here at the zero offset position. And what you can see here, these high amplitude features in here are surface waves, which are actually spatially aliased, as you can see in here. Now, in order to actually suppress these surface waves, what people typically do is they rely on array processing techniques, such as FK filtering or tau-P filtering. And to successfully apply those to filter out the surface waves, you would need to accurately sample these waves in space, which means you need a very dense sampling in the spatial direction here. So a lot of sensors. And typically the surface waves are, of course, the features with the lowest velocities. So they have the shortest wavelengths, which means that surface waves typically dictate the sampling in land seismic exploration. And as a result, these land seismic exploration campaigns are actually huge undergoings. And you can see just a picture here of such a land seismic exploration campaign in the Middle East, which typically involves a couple of 100,000 of geophones, over 10,000 shots are done per day. So this whole camp involves over 200 people, and all of this moves within months. So this is extremely expensive, of course, and any way to reduce this kind of field effort would, of course, be highly appreciated. So what we do now is we try to apply this wave type fingerprinting and separation scheme to remove surface waves locally with just a single station. And for this, we're going to use a synthetic case because there's really no real data, large-scale data set available, where we have real recordings of rotational and translational motions. So this would be then this seam model that we're using to generate this synthetic data set, which is quite a complex model where we have a lot of scattering from karstified areas here. So which means we have low velocity surface waves, which are aliased, but also scattered intensely. And these are typically very difficult to suppress with just conventional techniques. So this is then the data for just one source here located at this part of the model. And we have then a receiver line with 6 component receivers here. So you can see the 6 component data here on the right. And the surface waves here are the high amplitude features again, which are spatially aliased. And we now apply this separation technique to really try to remove these surface waves from the data and hopefully don't do any damage to the underlying reflection signals that we have in here. So what you can see is there's this one hyperbolic feature in here in this data set, which is actually a reflection. It is not a real reflection. It is one that I artificially added on top of the data afterwards, just to help you better visualize a bit what is going on, what we're doing. So this is before the filtering. Now this is after I try to suppress surface waves using this technique that I showed before. And you can clearly see that we remove this surface wave noise quite accurately. While if you're really looking at this vertical component here, we preserve most of the underlying reflection signal here, which is of course what we want. Now the advantage is again that we do this filtering completely locally, so there's no spatial sampling requirements here. This method can deal with side scattered waves because we basically train our classifier to be to to be independent of the propagation direction of the wave. So it can identify these waves coming in from either side. It doesn't matter. And unlike three-component polarization filtering, we can actually also identify Rayleigh waves that are close to linearly polarized, and also LOF and SH waves, which could pose a problem to some of the horizontal component analysis. And now this is just basically the part of the data that we removed here. So you can see that this is basically the estimated surface wave component of this data set. Yes, and then there's this final third example that I want to show here, which is related to the analysis of ambient seismic noise. And I'm looking at this data set here, which was actually collected in the city of Munich, so close to the city center, with a combined, or with this setup here. So we have a three-component fiber optic gyroscope, a blue-sized sensor mounted on the same base plate as a translational conventional seismometer here. And I took this data set actually from Sabrina Keil from LMU Munich, who was kind enough to actually provide me with this data. And what I want to do is actually try to apply this fingerprinting scheme now to this ambient noise data set, where you can see here 1 hour, I think it's 1 hour, yeah, 1 hour of noise here of translational and rotational motion. So this is then the fingerprinting result that I plot here just for one frequency here, so at 14 Hertz. And now each dot in here would correspond to the detection of a specific wave type in this 1 hour of data. And basically this gives you quite a simple way to really get an overview of what are the wave types that are contained in this ambient noise wave field that we have. So you can see that this wave field is mainly dominated here, or seems to be dominated mainly by Rayleigh and SV type of motion, but there's also some SH and LOF waves detected, and some P waves as well. And I think this is really unique, as in this is really not easy to achieve with any other kind of method, and we really don't know yet exactly what this implies, what information can we get from this composition of this wave field. Now here, this is just a frequency-dependent, basically, composition of the surface wave component of this wave field. So you can see that here at high frequency, the wave field is very much dominated. The surface wave field is very much dominated by Rayleigh waves over LOF waves. And then it seems to change a bit towards lower frequencies here. So basically, the sources that we expect here will be mainly urban noise, so traffic, road, but also construction sites and so on. And now, once we know the wave type, actually it is quite simple to then also estimate the phase velocity and additional wave parameters from this data. And for example, we can estimate the Rayleigh wave phase velocity with this very simple relationship between the vertical acceleration component and the transverse rotation component. Or we can estimate the LOF wave phase velocity with this simple ratio here. I guess most of you have probably seen these equations before. Now, I think it is really important to mention here that these equations would actually be quite meaningless if we wouldn't know what wave type we're looking at. So if you're just looking at random noise, for example, of course, the ratio of the vertical acceleration to the transverse rotation will not give you the Rayleigh wave phase velocity. So I think this kind of initial step of wave type classification is quite important. Of course, we don't have to necessarily do this with this kind of machine learning classification, but for example, what people have done in the past is just trying to assert that there's a linear relationship, for example, between these components to really make sure that we're not looking at just noise or other wave types in here. And then we can use these ratios, plot these ratios, of course, for each of these windows where we estimate or where we detected one of these wave types. So here I do this for LOF and Rayleigh waves, which basically gives you dispersion curves that are estimated from just this single station very locally, and just from looking at random noise. So you can see the clear here dispersion characteristic that we would expect, where we have lower velocities at high frequencies, and then we get higher velocities at lower frequencies. You can see here that below 5 Hertz, this this curve seems to drop off quite rapidly. And the reason for this is probably that we don't have any sources anymore here at this low frequency end. So this is really a way to extract near surface velocity information with very minimal field effort, which I think is quite attractive. And then an important thing to mention here is that this velocity information is truly local, so we don't smear out our information over the array aperture as we would do with conventional array analysis techniques, of course. We can apply it to quite short time series, given that we have sources active in this time period. So this actually provides us with a way to almost in real time estimate local near surface properties, because also the processing time is quite short, of course, with this classification that I'm doing. And what I haven't shown before yet is also this additional information that we can extract from the 6 degree of freedom motion, because we can also determine whether the Rayleigh wave motion, for example, is prograde or retrograde, which could potentially give us additional constraints on the subsurface. So you can see here that we estimate mainly negative ellipticity angles here for the Rayleigh wave, which means that this corresponds to retrograde motions here. So this already brings me to this summary. So just what have we seen today? So what I've shown is this way of fingerprinting different wave types based on 6-component polarization analysis, and we can use this then to separate seismograms into different wave type components. The applications that I've shown are, for example, automated arrival picking, facilitated phase identification, the suppression of aliased and side-scattered ground roll in land-seismic exploration, but also the estimation of near-surface velocity information, for example, from ambient noise recordings, and the composition of the ambient noise wave field in terms of wave types. Now, I've gone over some parts here quite quickly, probably. So if you're really interested in all the math behind it, I would like to point you towards this preprint that we've uploaded to archive here. So if you're interested in all the details, please go over there and look at this. And we've actually also published codes to reproduce all of the examples that I have shown today. So I've actually many people actually also involved in SPIN. We have made an effort to actually centralize wave field gradient applications, software, and so on in one place with this software package TwistPy that we have published very recently. And of course, we're always happy to have new users that test this package, but also since you are all SPIN students, or many of your SPIN students, of course, if you develop new methods, it would be really great if you could also contribute to this package, so that we have a centralized place where we can have all of our codes for wave field gradient rotational data analysis, so that we can really bring across or make it easy for people to use our techniques that we are developing. So I would be really happy to accept contributions from all of you to this.